Today we're going to look at our heating curve chemistry problem. This kind of problem typically involves converting from a solid to a liquid to a gas. The substance in question can be water, but it can be a variety of other substances as well. What all these problems have in common is heat must be added to our substance in order to produce a phase change. Now, it might seem a little excessive to have a whole campfire, but thanks to Prometheus, who actually stole fire from the gods, we have a whole variety of means in order to supply heat to a system. Could be a Bunsen burner if we're in the lab. It could be our gas stove, or it could be the campfire like we see here. Why do we need heat in order to make a phase change? Well, if you consider the different phases of matter, it's clear that in the ice phase, molecules are held together in a very rigid lattice pattern. Heat comes in and helps to break these molecules apart by increasing their motion. If we add enough heat, we'll get to the water phase, where the molecules are more free to slide past one another. And if we continue to add heat, we will make it all the way to the gas phase, where the molecules are in fact quite far apart and are engaged in rapid and random motion. In order to do a heating curve chemistry problem, where we are adding heat progressively to take us through the different phase changes, it is quite useful to have a heating curve that looks like this. This is a heating curve for water, and typically it starts somewhere below 0 degrees centigrade. And if we add heat, we will see the temperature rise. Heat is being added on the x-axis here. We will see the temperature rise on the y-axis until we get to the melting phase. The beginning of the melting phase, we're all solid, and by the end, we're all liquid. Something interesting to note here is the temperature during the phase change is steady. It is not changing. Once we have all liquid and we're continuing to add heat, now the liquid water will start to heat up until we get to 100 degrees centigrade, at which point we have a second phase change. Again, the temperature levels out, and we start from all liquid, becomes a mixture of liquid and gas until we have all gas, and then the heat can rise. The temperature can rise again. Now, a typical chemistry problem is we have a given substance and a given temperature transition, let's say A to B. Your mission is to calculate the total heat change for the given transition. Let's return to our diagram and consider a specific heating curve problem that includes one phase transition. The problem itself is this. We have 100 grams of water, and we want to calculate the total heat change, which we refer to as Q, for heating the ice from minus 10 degrees centigrade until we get all liquid at 30 degrees centigrade. This is going to require us to perform 3 separate calculations for Q. We're going to need 2 different equations, which we'll be looking at in a moment. So what are our 3 calculations? Well, the first one is going to involve calculating Q for the temperature increase from minus 10 degrees to 0 degrees centigrade. On the graph here, this is represented by the purple arrow. The next calculation is what we call the phase change calculation, which is this steady temperature portion of the graph where we actually have melting. And then the third calculation is going to be the increase in temperature of our all liquid water up to 30 degrees centigrade. Now we need to get prepared because, as noted, we need two different equations, but we also need some constants. Typically, these constants will be given within the problem itself, or you will have to look them up in a table. The two equations are Q equals ms delta T, and the second one is Q equals N times the molar heat of the phase change. Let's review what all the variables are in these two equations. M is mass. S is what we call the specific heat, sometimes written as a lowercase c. You'll see it both ways. N in the second equation is the number of moles. And then delta H, again, is the molar heat of the phase change. For this particular problem, we're going to need at least three. We're going to need three different constants. We're going to need two different ones for specific heat, and we're going to need the molar heat of fusion, or the enthalpy, which is the heat required for the phase change of melting. So, why do we have two different specific heats? Well, the specific heat of ice is different from the specific heat of liquid water. Actually takes a bit less energy to raise the temperature of ice than it does liquid water. That's why we have two different specific heats. We can now do the actual calculation for the specific problem referenced earlier. We have 100 grams of water, and we want to calculate the total heat change, or the total heat we must add, in order to heat ice from minus 10 degrees centigrade to all liquid water at 30 degrees centigrade. We're going to utilize our two different equations, Q equals ms delta T, and Q equals the number of moles times the molar heat of the phase change, in this case, melting. Our first calculation is going from minus 10 degrees to 0 degrees to get to just the beginning of the phase change. This means we take the mass, 100 grams, times our specific heat for ice, times the change in temperature, 10 degrees Celsius, and we get 2060 joules. Converted to kilojoules, this is 2.060 kilojoules. Next up, we have the phase change. We have all solid ice at 0 degrees centigrade. The temperature remains steady during this phase change, and we end up with all liquid water still at 0 degrees centigrade. This requires us to use our second equation. Q equals the number of moles, this is our mole calculation here, times the molar heat of fusion, that is melting. Since the units of our molar heat are in kilojoules, we don't have to make any conversion into kilojoules. It's already there, 33.41 kilojoules. Third and final calculation. Q3 is going from 0 degrees centigrade to 30 degrees centigrade for a delta change of 30. Still 100 grams, but now a specific heat for liquid water. When we do the math, we get 1,255 joules, or 1.255 kilojoules. Notice in the first and third calculations, the reason we get joules initially is the units of specific heat are joules. Now, in order to get the total heat, we simply add these three numbers together, and we get 36.7 kilojoules, three significant figures, as is appropriate to the problem. Victory is ours. Victory can also be yours if you go online and you look for the many, many problems available there to get a little practice. You will also get practice on the homework, in recitation, and then ultimately be prepared to tackle this problem on an exam. Go forth, practice, prosper, and thank you for listening.